I have 3 talks in 30 minutes. It'll be awesome. And recently I've ported our client protocol to Erlang. So no Node.js today. Everyone go, yay! Yay! Boo! Okay. Who here has heard of the 4 V's of big data? Except me. No answers. Hands up who has. Okay, so 2 people have lost their voice, everyone else hasn't heard of it. Excellent. Okay, so volume, velocity, variety, and variability are classed as the 4 basic aspects of big data that most people care about. They're wrong. It's about value, right? There's no point in me sending you data that's already too late. It's already stale. I've already got an extra price. I've already got a better price for IBM, one that happened right now. So any data on the internet in those buffers causing buffer bloat is stale. It's useless to you. It's not tradable. You'll end up losing money on the basis of it. So we excel in solving that one problem. So Basho and React give you eventual consistency, and it's extremely available, right? I give you immediately consistent, or at least that's what I try to do. So that's what my company does. And that's what I'm going to talk about today. So what's a minute on the internet? Intel did a really good infographic about, was it last year, Pablo? Where's Pablo? Pablo?
Going to get the edit.
It was last year or the year before. So you see there's 204 million emails sent a second. That's probably slightly more, maybe slightly less right now. 20 million photo views on Flickr, for example. These are fairly big numbers. But this is minutes, right? People are thinking minutes, hours, weeks, months. I come from a world where I think in seconds. So the closest analog I have to this, if you have, who remembers OMG Pop came out with Draw Something, they got acquired by Zynga. Right, they scaled from 6 to 90 servers in a matter of about 6 weeks, 9 weeks. Fairly good scale, okay? But ideal in this world here, speed. So you might have a 10K document delivered in a millisecond. I deal with 1K documents delivered in 100 microseconds or less. Okay, so 8 milliseconds to me is an eternity, okay? I'm dealing with a different level of speed, if you will. Okay. So the last mile is hard. It's probably the hardest mile a piece of data travels. It's the mile where you're on a train, you go under a bridge, you lose your connection. What happens with the data that's actually traveling through to you? What if you're trading on a horse race? What if it was in the last furlong of that race? And well, you're not going to trade on that race, right? Not in the dying seconds. So these are the kind of problems that I try to solve. So if you've got stale information, that's not going to work. So data needs to be recoverable. And this is all about delivering data to humans, okay? We don't react very fast. When you blink your eye, how long does it take for you to open your eyes and start seeing things again? Anyone have a guess? Says half a second. You need coffee. Okay, who says 100 milliseconds? You're really fast. You've had too much coffee. It's about 200 milliseconds. Okay? Just to blink your eye, your audio-visual system or your visual system shuts down for about 200 milliseconds. What focus do you actually have on these slides? Anyone? Everyone sticks their hand out, straight up. Come on, stick them out. Those of you that have them, 4 in the front have hands. Look at the end of your thumb and look at the nail. That's about as much as you have in focus right now. Everything else is a blur. It's gradual scale. Yet traders, with all their 6 Bloomberg terminals and their massive monitors, think they have finer superhuman acuity than anyone else. Right? Yeah. What do you think you'll notice in this backdrop of text that's actually changing in front of you? What will you home in on? Changing textual values? No. You'll notice color changes. You'll notice changes in shape. You'll notice structural changes much more quickly. So optimizing trader real estate is actually quite important. You've got 40 milliseconds it takes for you to notice these things. So can anyone tell me, is there any point delivering more than 1 second divided by 40 milliseconds worth of data to anyone ever? Unless they're superhuman, and the traders, of course. You might send them double. No, there's not. So why are we sending them real-time data using messaging systems and clogging up the internet? We think that's silly. We think that's something that was invented years ago when there was no internet. Right? This was developed behind the firewall. We're just using it in front on these global networks. That doesn't make any sense. Anyone remember Digital Equipment Corporation message queues? Horrible stuff. Not worth remembering. Okay, fallacies were simple in those days. The network was reliable, it was small, it was monolithic. Okay? Latency was zero, it was going from your desk to your desk. Didn't have anywhere to go. It was speed of light, it was awesome back then, between A and B. The topology never changed because you couldn't afford another machine, they were the size of this room. It's true. Then in 1992, the internet happened. The first SMS was sent in London. Everyone go, them were the days. Most of us here are old enough to remember. And it was good, so it grew and it grew. Then in 2007, the God phone happened. Surfing died. I'm sorry, Gene Polly. Surfing is gone. Now we're touching the internet. We want to get our hands on the internet. The internet was awesome in 2007. So we took everything and we stuck it inside the internet. The cloud happened. Okay? So we could touch all of the things. And now everything was in the cloud. Brilliant. And it grew like all the good things do. So we scaled all the things. Things like React came about. It was about 2008. You started about fairly early on then, right? So React was fairly quick onto a good thing here. Okay? Oh. But bad things happen if you're human. This is good for systems. Who here does not use Twitter? Put your hands up. Liar. 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 Okay. Twitter. Who's ever been on Twitter, right? And you're tweeting away while you should be working. You're avoiding work as usual. Okay, you're there. You should be compiling something or testing something. Who cares, right? Twitter's more important. You tweet something you think it's really cool, and then Twitter says, "Whoa, you've already sent that." You go, "No, I haven't. I'm pretty sure I just sent it once." So what do? You try to send it again, right? Who falls for that every single time? Yeah. So you click on tweet and the same message is there, you try to send it again. What happens? Whoa, you've already sent that. Now it's true the second time. But the first time was annoying when I know you got it, but the second time that you reminded me, that immediate inconsistency is a big problem. Twitter, the bird, immediately inconsistent, but eventually consistent, maybe. We're not sure, right? That's really annoying if you're a human. It's okay if you're a system, you can be eventually consistent, you can mop that up later. But I'm not built like that. Okay? I want immediate consistency. I want it to always be current, because the real world for us is, well, the network is not reliable, right? You go under a bridge, goodbye network. It's that simple. Bandwidth is not infinite, nor is it fair. If you're on the O2 network versus telecom, here, it'll give you a different grade of service. Well, not here, it'll give you no service whatsoever. Okay? So what do we do about this? Well, we look at the business values and trust around this to solve the problem. In other words, you measure everything. Okay? So we look for nuances and trade-offs. If any of you have been to a lot of Basho talks, they talk very well about nuance and trade-off in database systems. So I'm going to do the same for messaging. Or should I say, for not messaging over the internet. Okay? And I think it's about these things. So is it relevant? Right? A gambling price or a trading price is only relevant right now. As soon as another price comes in, it's irrelevant. It's old, it's stale, it's dead, it's gone. Okay? Responsiveness. Using HTTP or REST. Right, that poll sequence, dead, it's gone, it's already late. Okay? Me waiting for a response, there's other data backing up I could be requesting. Okay? So that doesn't work. So it has to be streaming, it has to be asynchronous. Timeliness. Well, that depends. If you're a system, you have all the time in the world, but the systems that I build, even for humans, are mission critical in terms of you don't want to wait. You want to gamble on that price right now. And it's the same in a lot of the real-time kind of machine-to-machine systems, the algo trading engines I've built. Right? It's all about current delivery of data right now, and it has to be consistent. Okay? And then context. If I have 100,000 messages, and you're on a 3G network, why should I send you 100,000 messages per second? Right? If you're on a 3G network, you can't receive 100,000 messages per second. That's impossible. Our solution doesn't send you 100,000 messages per second. It doesn't even try. That's intelligent. Okay? So how do we do this? If you take messaging, you've got producers and you've got consumers. So you've got queues on each side in a regular messaging system. But what if we take the queue on the client side and we move it over to the server? Right? So we host the client-side queue on the server side. What does that mean? Well, what's the bad thing? What's the downside first? Well, there's no damn queue on the client side, right? So it makes guaranteed delivery more difficult. Fact, right? But I've now got telemetry on the server side. If I can't send a particular client data fast enough, that queue backs up, and I can do something about it. I can start conflating. Because I can see it's backing up. For some reason, I'm not getting the data out to that client or that set of clients. I have a chance to actually do something useful about that. Okay? So what if we add data caching inside a messaging technology? So you've got, say, a topic-based hierarchy. Okay, what if I start caching data inside that? Well, then you're one hop closer to the data. Surely in a distributed network of systems, that's a good thing to do. Okay? Because you're one hop closer to what we hope is consistent data. Next, exploit the data structures. So don't send opaque data types around the place. Instead, take a snapshot of a data structure and send that. So if I have a list and you connect and you subscribe to my topic, I'll send you the list. But if I add a thing or remove a thing for the list, I won't send you a new list. It's not immutable, right? Everyone goes, oh, immutable is brilliant. It makes life easy. Not if you're a wire. It makes it bloaty, okay? So you send what was added and what was removed from the list. And you can merge that then on the other side. So you can reflect these data changes over time through the system. Okay? Make sense? Nothing shocking here. Shocking comes later, so that's good. Awesome. Okay. Behaviors. So although our server is implemented in Java, this is kind of Erlang style. So you can deploy a behavior, a piece of code inside our messaging system to change the way the messaging system works. So if I was receiving a bunch of log files, say from Log or from a React system, I was pushing them in some way using our client protocol, I could push them in, and this kind of what we call a publisher can take that data, maybe filter it using a complex event processing algorithm, and then send the result set further downstream. In other words, we can reduce that to a flow of information you might actually be interested in. In most high-frequency systems, you don't care about things that are within trend, right, that are within certain thresholds or norms. You only care about the things that go out of trend. Okay? And that seriously reduces the amount of data you're sending around the system. A good trick if you're just about to build your first real-time system, the things that are going within perfect tolerances, ignore it. You don't care. When it doesn't, then you care. Okay? Structural conflation. Structural conflation is where between the queues that are hitting the topics and each individual client queue, because we have client affinity, we can do something structural with the data. So in most messaging systems, if it conflates, it replaces an old value with a newer value. Let's say the operation semantically you were doing in a system was adding things, or counter, or doing profit and loss. I can take a piece of data that's about to hit the queue and a piece of data in the queue, and I can add them or subtract them. I can structurally conflate the information. If it's a map or a list, I can merge them in some way. Right? And if another data item comes in before I get a chance to send it down the wire, I'll merge that too. In fact, I'll do that so aggressively, I can save a lot of bandwidth. The slower you are, the more I work for you in sending you current information. It's never stale. Okay? So that's what I do for a living. But I'm interested in CEP, and this algorithm is a very CEP-ish-like algorithm, okay? So you can see where if I have an operation, I have 5 values, say, in the queue, and I'm merging under summation, then if these two are destined for the same topic, I can conflate that into one update, right? I just add the numbers on the server side and send you the result. Of course, it could have been 10 or 15 or 100 updates. I still only send you one result, but it's still consistent with the intent for that particular topic. Now, it has to be a topic that can take that. For example, if I have a topic that needs to be distributed forensically where you need auditability, I can't do that. Right? The data is wrong. Right? The business value isn't in the data. Does that make sense? If I need audit control or storage, I need a forensic record of everything. I can't conflate the information. I have to send you everything. There are surprisingly few of those use cases. Most use cases, you can actually conflate heavily the information that's going over the wire. And now it works in Erlang. So this is a client, and pretty much currently looks like this. It's in alpha. Ping me if you're interested. And it works with Lagger as well. So I can, as I mentioned earlier, just have a little Lagger back end here, and that will take my message and send it off to my in-memory system. So if I have a big React cluster, I can send in, say, fatal information or errors and pop it into my messaging system, do some further analytics, and then pop the results set out onto a real-time dashboard. Right, so as it is logging, I can pull stuff in. Okay, first talk done. Second talk. Oh, that was the easy talk. They get harder. Okay, so.
We're about to fall asleep.
Okay. So let's measure this. Okay, that's great, but let's measure the value of this. And warning. Okay, performance is not a number. A lot of people come out and they say performance is a number. Like at 1,000 bytes, our performance will be like this or like that. Right? I'll give you a range of numbers so you can see a characteristic profile of performance rather than a single monolithic number I picked because it works ideally with what I'm showing you. I'm going to show you a range. And it's just throughput and latency benchmarks between two boxes. Okay? It's a very simple throughput case. So we're adding 750 clients on I think it's 3 or 5 second interval until we hit saturation on the network. So there's 10 gig cards between these machines. And then we look at what happens after saturation. Right, because something's got to break, right? Most people test up to or near saturation. We test beyond saturation. We're more interested in, it's going to fail. Where will it fail and why? It's much more interesting. Okay, so let's have a look. We do have a very simple latency test. Single client, send a message, get a response, divide it by 2, there's your single hop time. Okay? So it kind of looks a little bit like this. So we've got from 125 bytes on the small side to 2,000 bytes. You can see for 2,000 byte messages, it saturates pretty quickly into the test. So in about 40 seconds into the test. For 125 byte and 250 byte messages after 5 minutes, it's fine. It hasn't saturated yet. Okay? Makes sense? This is the server-side view. Here's the client-side view. So this is what the clients are seeing for this as we're ramping in. So when we hit saturation here, you can see for this large message size, I think it's 2,000 bytes, this very strange waveform. So what's happening? Okay? I've been ramping clients continuously, another 750, stream data, another 750, stream data until I hit saturation. I'm still chucking clients at the problem. So what do you think happens? I stop serving the newer clients that are coming in. They time out and they drop away. What happens when they drop away? I've now got more space on the server for more clients, so they start joining again. And it goes back up. And it tends to take a while before it settles, right? And it reaches a steady state. But it's still obviously not very happy, right? You can see you're getting quite a lot of volatility in the messages receiving on the client side. This is the client side view. Okay. So here's it with conflation, okay? So you can see it takes slightly longer to saturate in this case, but the interesting view is on, right, the client side. You see it stabilizes very quickly into a stable state. In other words, the server notices and it starts conflating the data massively because the queues are backing up. Conflation kicks in. Right, so when you're not saturated, it'll send you data as fast as it can. Here's more up-to-date data. Here's more up-to-date data. As soon as it's saturated, it goes, oh, hang on a minute. This isn't good. So it starts to throttle down in terms of how many pieces of data it's delivering to individual clients so that everyone gets a fair service. So you go from 100 to 80 messages per second, but you're serving 45,000 clients. It's not bad, okay? All right. So let's have a look at latency. Okay. So here's the latency profile. You see it's nice, tight and to the left. It's a log-log graph. Tight and to the left is good. Outlier, not good. Just 2,000 bytes. Sorry for the different color. More interesting stat is, to skip these, is this range. So for single hop latency, it's 8 microseconds about as good as we can do. To 50 microseconds for the higher message sizes. Quite a high degree of variance. A lot of that is garbage collector inside the server side. The fastest you can get in Java today with a simple producer-consumer kind of ping-pong test is about 5 microseconds. Right? The fastest you can do that I know of with commodity hardware is 2.4 microseconds. If you can do it faster than that, let me know. A, I won't believe you. B, I'll want to see it. But that's the fastest I've seen with commodity hardware. Okay? Just commodity 10 gig cards. It is capable in C or assembly to get between 2 boxes in 2.4 microseconds. Without breaking much of a sweat. Okay, into the third talk, you'll notice that I talk a lot about processing events. Well, what's the important thing in delivering consistent information currently to the other side? Deciding what to send? Or deciding what not to send? It's deciding what to drop. It's deciding what is not important so that you can put all of your resources and energy into what matters. And that's very use case specific. It's not something you can build in a framework and pre-package and go, it's here, the solution. Wrong. Right? You need to pick for every single individual business case and pick something that makes sense for that case. If I have data that requires forensic storage, I can't drop that data. I can't conflate it. I need individual transactions to record. Okay? But if it's recoverable data like prices, if I drop the connection and I connect on the other side of the bridge, I'll just get more prices. It's recoverable. So that's sacrificial data. I don't care about that. There's more of that. What about the order and trades, the bets on the way back? I don't want to lose any of them because those bets and orders won't happen again, and I want to have a platform that's very successful, and I'll go out of business. That's probably bad. See? Business value of technology is how we all get paid. And some of the techniques for that come with event processing. And that's kind of what I've been doing for the past 10 years. So CEP, basically, you've heard it kind of loosely with Storm and React pipes, is input streams and output streams in my worldview. There's map operations, not to be confused with map in a functional language like Erlang, but map takes in some record, you apply some transformation to it and it returns a result, one for one, through a map. You've got windowed operations. These are the most interesting. So I've just implemented these in Erlang, so I'll show you that now. You can branch things, combine things, and you can store stuff in memory. Well, Erlang's a language, so we've got GenServer to solve this problem. We can branch and combine by writing code, so that's not a big problem either. And, well, map and other kind of transformation operations. We've got an entire language to do that. But there's no real good support for windowing in most languages, so I decided to add that. This is the hard bit, by the way. Brace yourselves. Okay. This is an aggregate function. So Francesco in his talk earlier mentioned behaviors. This uses a custom behavior. So you're not limited to the set inside OTP. You can generate your own for whatever you want to do. So I have one for something called an aggregate function. And it has an initialization function with no arguments, an accumulate method with 2 arguments, a compensate method, which we'll get into in a minute, with 2 arguments, and an emission method. So when a window closes, it emits a value, right? A window is just a subset of streaming data that's in memory at a given point in time. And I'd implement it like this. So this is a max. Right? So I'm getting the max of 2 values. I've got the value in the window and the value coming in. I just compare. And if it's a bigger value, then I store it. If it's not, I drop it. Okay? So I store over time, over the period of this window, what the maximum size value I saw streaming through the window. It can be any arbitrary type. This one works with or assumes numbers. Okay? So that's how you implement it. And I apply this function that I can write once and reuse. And that function could be standard deviation. Get me the standard deviation of something, the variance. I write that function once and I never write it again. I just point it at a window and the window pops out values. So the different window types I have, plus the different functions I can plug in, give me a compositional value that's greater than the individual parts. So in a tumbling window of size 4, I will receive 4 events, calculate an average or a standard deviation, and pop out a single result. Make sense? Pretty simple. It's non-overlapping. You've got a discrete set of 4 events, a discrete set of 4 events, separated over time. Very simple. So it might look like this if you were to do that inside the REPL. Sliding window, slightly more complicated. In a sliding window, say for 4 events, I'll receive the first 4 events, and on the 4th event I will send you a result, average, standard deviation, whatever. On the 5th event, this is where it gets hard, by the way. On the 5th event, for that and the past n-1, 3 events, because we have a size of 4, I will give you the standard deviation or average for the last 4 events from the current event that's just going out. But there's an event coming in, which will be in the next result set. Got it? Make sense? So once the 4th event comes in, on an event-by-event basis thereafter, I'm sending you a result set that's based on the last 4 events historically from that event in time. Got it? Picture yourself on the road inside the car. It makes perfect sense.
Sorry, could you repeat?
Yes, later. Right? So over time we have 4 or 5 events, but I'm always counting back through time, right? So in other words, I'm back propagating the current value into the last stored partial results so that I can give you some derivative results at the end of the window. But every time you receive an event, once you get to the size, you're always producing a set of results. In other words, over time you have a set of events, and across the size of windows you have open, you've got a set of events, so it's n times n-1, it's exponentially degrading. How do we fix that problem? Well, you notice I had a compensate method. Okay? So rather than backpropagating those result sets, I can compensate by going, what event am I about to throw out the window? And what did I do? I added a thing. Why don't I just remove its effect rather than backpropagating a new set of results? Make sense? Now it's linear in performance. I was shocked when I discovered that. I was literally in bed asleep. I woke up and said, it can't be that simple. I ran downstairs. It was that simple. I was shocked. Right? Mostly, this is the compensate function. Right? So if you go back to the aggregate, right? It's exponentially degrading. You amortize the effects over time, but if it's high frequency, you're getting this set of events continuously. So you have the continuous set of events, which is one dimension, and then you have the back propagation across the set of events, which, for the number of open windows, is exponentially degrading. Now imagine you're running an exponentially degrading function inside the window. What if my calculation is a Fourier transform? I've now got, I'm exponentially degrading by algorithm, and I'm running an exponentially degrading algorithm. It's doubly exponentially degrading. I think the technical word for that in computer science is you're buggered, as n increases. Okay? It's true. That's the technical term. Look it up. I'm not lying. Okay. So, we can backpropagate a set of results or add a function to compensate. So as a value or result gets evicted for a window that's no longer relevant, we kind of subtract, we rub away its effect on the windows that are open. Make sense? So I have a simple computation as a cost rather than backpropagating it through a set of results. That gives you linear performance. Okay, kind of looks like this. Periodic windows, so every second emit a result set, quite simple. And monotonic windows. In a monotonic window, you have, well, like a periodic window, except NTP doesn't bugger your notion of time. So if you had a vector clock, you could plug it inside here. So when a certain number of vector clocks, quantums, have passed, you can do a thing, whatever that thing happens to be. You can plug in your own clock implementations. There's a behavior for that. Okay, kind of looks like this. It's really, really simple. Okay, so I call this EAP. Right, I've got another project. This is in Node.js. I've got another project I call Beam, Beam, the Erlang E-terms. The Node crew didn't notice. But EAP is now available in Erlang. And also, Ian Barber, who hangs around the PHP Erlang communities, wrote one in PHP. So now it's available in JavaScript, PHP, and in Erlang. I stuck that on GitHub last night. So it's available there. Enjoy it. That's my talk, or my 3 talks. Are there any questions?